So this, what you're looking at right now, is an old reaction that we've done already. This is, the acid catalyzed hydration. We're going to take our alkene, react it with water, a little bit of catalytic amount of acid. So go ahead and pause the video, see if you can draw the mechanism for how this reaction goes. And then once you get the mechanism, then you can unpause it and we can talk about it a little bit more. Okay, so the first step is going to be that alkene, the double bond, acting like a base. It's going to be pulling a hydrogen just from hydronium or any kind of other acid that we might have in solution. Classically, the acid that we use is just H3O+. And so what we're going to have is we're going to form a carbocation. So we'll form our carbocation. And that carbocation is going to be at this position right there. We prefer this position over the first. Actually, let me number this guy: 1, 2, 3, and 4. We prefer to put that hydrogen on the first position and not the second, because if we put the hydrogen on the first, we get a secondary instead of a primary carbocation, which is great because we maximize stability. So at this point, some red alarm bells should be going off in your head about trying to do rearrangements, trying to always stabilize, a carbocation to be something a little bit more stable. So the only time these, red lights shouldn't be going off in your brain is if you already have a tertiary. So what we're going to try to do is stabilize this carbocation. We could try to do a 1,2 hydride shift. So we could try to do a 1,2 hydride shift. And in that case, we could try to move one hydrogen over, just like the pawns in chess, and we could try to stabilize that carbocation. But really, the only hydrogens that are vicinal to this positive charge are right here. And if we moved one of these hydrogens over, we just get a primary carbocation. And that's going the opposite direction. That's going less stable. So, and then if we look one other vicinal position to the left, in this case, this carbon in blue, this guy has no hydrogens attached to him. So we can't really do a hydride shift, but we could do some other kind of shift. So we could do, instead of a hydride shift, we could end up doing a 1,2 methyl shift, and that would be just fine. So let's try and do a 1,2 methyl shift and see if that might help us out at all. So if we do this 1,2 methyl shift, we can draw an arrow to the right to indicate that we're going to change the molecule. So I'll redraw the molecule, just like this. And now we're going to have an extra carbon over there, and this is going to be our positively charged carbon. So 1, and then 2, and then 3, and 4. And so again, this is going to be 1, 2, 3, and 4. And so now that positive charge has moved from 2 to 3, and let's say this is carbon 5. Carbon 5 has moved down over here. So 5 is now attached to 2, and 3 still has, 6. 3 still has 6 attached. So now, if we wanted to go through the mechanism and complete it, at this point we've kind of done the hard part. We can have our water act as our nucleophile; it can attack, and then at this point we get a new oxygen to carbon bond. That new carbon is carbon 3. That's the bond or carbon that's going to have the oxygen attached. And we have to make sure that we draw both of our hydrogens because we haven't broken any of those bonds quite yet. And just going to complete the molecule. And then we're like 99% done. All we have to do is now have a little bit extra water coming in, acting as now a base instead of a nucleophile. You can rip off a hydrogen and you can have that bond breaking. And so then at the end of the day, we'll get this molecule right here, OH, on the third position, so 3 and then 3. And let me just finish up the rest of the molecule. I'm going to erase this part so I can draw my methyl group a little bit clearer. So there's my methyl. So that's position 2, and then carbon 1 and 5, and 1 and 5. So let me move this guy up a little bit. Redraw my reaction arrow. And so now this would be one final product. So what if we really wanted to have that hydroxy group attached to carbon 2 and not to carbon 3? Because right now, according to this mechanism, we know that this is going through a carbocation mechanism. And because of that, it can do these shifts. And because of that, this product is going to be our major product. And the other more intuitive example before we knew about these shifts, we would have predicted something like this guy over here, where we would have had the hydroxy on carbon 2 instead, and that that still might happen, but in this case, this is going to be a very minor product. So what if we wanted this minor product to actually be major, and you wanted this hydroxy product to be the minor? What if you wanted to switch it? So what if we really wanted this guy as a major, and what if we wanted this to be the minor? Well, there's an app for that, and the app for that is called Oxymercuration. So we can actually do this oxymercuration, and we would be successful at getting this product as the major product. And we would call this product the non-rearranged product, or the product that follows directly from Markovnikov shortcuts. So I'm going to go ahead and give you the reagents to do this kind of reaction, and we'll talk about it a little bit. So let's just copy paste this molecule from above, and then let's say, what if we really wanted to get this molecule with the hydroxy on the 2 position, and we want this guy as a major? Well, we're going to be able to do that with these oxymercuration conditions. And oxymercuration is a little bit complicated in terms of the reagents. We actually have quite a few new reagents that you've probably never seen before. So the reagents are going to be, this reagent up top is called mercury acetate. So mercury acetate, so this is a mercury atom, and this mercury atom is semi-covalently linked to this group right here. So 2 of these groups, and these groups are called acetate. And so if you're curious, the acetate groups kind of look like this, where you have an oxygen attached to another oxygen, and this little squiggly line is just kind of indicating where this oxygen is attached. So really you could say that this oxygen kind of is bound to a mercury right here, and then there's another oxygen attached to another part of the mercury right over there. So these aren't really formally covalent. They're more of a dative bond, where they're somewhere in between completely ionic and completely covalent. But either way, they're bound to the mercury. So you've got mercury and then water, and then a new thing that you've never seen before is this designation where you have a 1 and a 2. And what these numbers are telling you is that this oxymercuration is actually a 2-step process. So the first step is the mercury acetate and water, and then the second step is this new reagent called sodium borohydride. You have to remember that it takes 2 steps and not 1. And the first step is the addition of this mercury acetate, and the second step is the addition of this sodium borohydride. And after you add these 2 reagents in sequence, you get this final product over here, where you've got still an alcohol. We're still making alcohols from alkenes, but the cool part about the oxymercuration is twofold. One is going to have no rearrangements. So that's the first good thing. So no rearrangements. And then the second part is that you can categorize this oxymercuration in terms of Markovnikov. So what you're going to find is that for oxymercuration, these reactions proceed in a Markovnikov fashion. You can try to think about what we said with Markovnikov, which was that the nucleophilic portion is going to end up going to the carbon with the most substituents on it. So if you had to choose between putting, your oxygen on carbon 1 or carbon 2, it's going to turn out that carbon 2 is going to be your more substituted portion, and water at the end of the day is going to be your nucleophile. Now, it's not really that obvious at this point why water is going to be your nucleophile. To answer that question, you could actually go through the mechanism. But what's really nice is that we're going to treat oxymercuration as kind of a black box mechanism, where you don't actually have to understand exactly how the mechanism works to be able to utilize it. Okay, all you have to know is that oxymercuration, you have to know that they don't do rearrangements. You add an oxygen in a Markovnikov fashion, and you have to know these reagents. And so if you're really interested, go check it out. It's really cool, but it's on 180. But other than that, I'm not going to test you on it.